Okay, now that we have the basics of number systems, let's look at how we create logic that manipulates binary signals, or specifically combinational circuits. So what does a combinational circuit compute? Given some binary inputs, signals that either are 0 or 1, the combinational circuit can produce some outputs. In this case, we'll say one output, which is also a binary signal, either 0 or 1. This is also called a black box model and is one common way that we'll model the hardware, the digital logic that we create, specifying the number of the inputs and the output signals. Now, one of the ways that we can specify the relationship between the inputs and outputs is with something called a truth table. And a truth table simply lists all the possible input combinations and their associated outputs. So we'll tabulate all the inputs, possible inputs A, B, and C. And these can be in any order, but usually we put these in the numerical order, 0 to 7, for 3 inputs, and then the associated outputs, whatever the outputs are for a given input. So for 0, 0, 0, if the output's a 0, then we put 0 here. For when the inputs A, B, and C are 0, 0, 1, and if the output's a 1, then we'll put a 1, and so forth, listing out all the outputs for the corresponding inputs. Now, given there are only 3 inputs and each of these are binary, we have now explicitly defined the relationship between the outputs and expressed what this particular combinational circuit, what it does with the truth table. And so this is a very important tool that we'll use for designing combinational logic. Okay, so now let's talk about Boolean algebra, which is an important set of rules which govern the basic operations and how we construct those to make digital circuits. So Boolean algebra was created in the 1800s by George Boole, and it also has a rich history and a connection with many areas, including in philosophy and logic. Now there are 3 basic operations in Boolean algebra: and, or, and not. The AND operation has 2 binary inputs x and y, and the output of an AND of those 2 signals is only 1 when both of the inputs are 1. It can also be described using the operators that looks like multiplication, or simply with 2 variables, binary variables, together like this. And sometimes in other logic text, you may see it written with this caret symbol. Another operation is the OR operation. Also takes 2 binary inputs. In the case of the OR, the output is a 1 when either of the inputs are 1 or when both of them are 1. So 0, 1, 1, 1. The OR operation is also can be written as with the plus symbol, or again in more other mathematical notation looks like this upside down caret symbol. And then the third important operation we have takes 1 input. It's a unary operation and is the NOT. And the NOT simply is the inverse or the opposite of what the input is. So if the input is 0, the output is a 1. And if the input's a 1, the output's a 0. This is also called a complement, and notation that we'll use for this sometimes we'll see as putting a bar over the top of it is equivalent to the NOT. And sometimes we also list this with a little apostrophe on the outside. This is also the same thing as the NOT or the complement. Okay, and so now with digital logic, we also have the notion of gates. A logical gate is just an electronic circuit that operates on 1 or more input signals to produce an output signal. And so these will be kind of our building blocks for how we put together our digital circuits. And for each of these basic Boolean operations, and, or, and not, we have corresponding gates and their symbols. The AND looks like this, 2 inputs, x and y, and then the output. An OR gate looks something like this. And the NOT, the standard symbol, look something like this, a little triangle with a circle on the output. Okay, and so here's the neat thing about these three gates. These mathematically are actually considered to be universal, meaning that I can construct any arbitrary function of any arbitrary complexity with just these three gates and connecting these together to form a circuit. So we'll come back to this more a little bit later. Now on PolyLearn, there's a handout that has all the basics for Boolean algebra. So at the top we have our truth tables for our three basic operations, their corresponding gates, and then we get into some of the fundamental laws of Boolean algebra, starting off with some basic axioms. And then we have some single variable theorems or kind of fundamental rules. And many of these are fairly intuitive, but they're important ones too. So for example, ANDing a binary zero with any signal will always give me a zero. And this is the null property. If I AND any signal with 1, that always just gives me the signal. Another important property, idempotent. If I AND a variable with itself, is simply equal to the variable. Involution or double complement, another important one. If I complement something twice or take them out of it twice, I simply have the same variable. And at the bottom here, we have many other properties. Some of these are familiar to us with our kind of algebra we learned in grade school. So if we take x and y is the same thing as y and x, those are kind of obvious, but some of these other ones are probably new. So absorption, combining into Morgans looks slightly different, but these are also very important Boolean identities. Okay, so now using these three basic gates, we can start to create some interesting combinational circuits or combinational logic. So this is an example of a combinational circuit or combinational network. And given this network of gates, let's say I want to figure out what this particular circuit does. So I want to write a Boolean expression for this circuit, another way that I can represent a combinational circuit or function. So I'm going from the combinational circuit to an expression, Boolean expression, simply by reading off from the inputs to the outputs. So in this case, I have y naught at this net. Then I have z or y naught. The output of this this OR gate is z or y naught. And then I have x or, and the output of this particular NOT gate is the complement of both z or y naught. And so I am ANDing x with z or y naught. And then finally I have one more gate, so I'm taking z or y naught or x ANDed with z or y naught. And I can also go the other way. I can also go from a Boolean expression to a combinational circuit. So for example, so I have y and z ORed together with 0. And then this big part on the left over here. So to construct that, I have y naught ANDed with this part on the left, which is an OR gate, ORing together x and y naught. And then the inverse of x or y. Okay, so now let's say that I wanted to see if two Boolean expressions are equivalent. How would I do that? Well, I can do one way to do this is with something called perfect induction, which basically means use truth tables. So, and I would like to verify if these two expressions are equivalent. And so one way I can do this is with a truth table. So I have three inputs, x, y, and z on both sides. List out all the possible combinations. In this case, there's 3 bits of input. So there's 8 possible combinations. And then I'll look at, well, I can break down the left-hand side into 2 pieces. So y naught or z. So when y is 0, then this expression will be 1. or if z is 1. So I have 1, 1, because y is 0. Then I have z is 0. And so for this particular expression, I have a 0. But when z is 1, I also have the output of 1. And y is 0. Again, these two right here. So I have 1, and then I have one more 0. Okay, and then this part, y naught or z complemented. So for this guy, actually let's put one more variable in here. So x ANDed with this. So when x is a 1 and this second part is true, then this value is a 1. So when x is 1 is these lower 4 rows. And then in this case, I'm going to have this expression be equal to 0. So z will have to be 0. That narrows it down to these two rows. And y will have to be 1. Well, that's actually only one row. So this guy right here. Otherwise, this will always be 0. Then I OR these two together. 1, 1, 0. 1, 1, 1, 1, 1. All right? So this is the left-hand side. What about the right-hand side? X or y naught or z. So here, whenever x is 1, so the lower 4 rows will all be 1. Whenever z is 1, so these two, and I have this row, and then this second row right here. And then when y is 0, so the first two, and these two are already 1, so it looks something like this. Well, now we can look at it and we can compare. So by perfect induction, we've listed out all the possible combinations, and the outputs for both the left-hand side and the right-hand side for either expression are exactly the same. Now, if we wanted to prove that these are not equivalent, all we would have to do then is find an example of a case where these are not equivalent. Okay, so now let's talk about how we go from a truth table to a Boolean expression, and then a combinational circuit. So given another example, three inputs, three binary inputs, x, y, and z, and then a function of these. So to do this, actually, it's one way to do this is fairly easy. I can read off what's called a sum of products, or SOP expression. And to do this, it's fairly mechanical. All I'm going to do is I'm going to look at each row that has a 1 in the output, and I'm going to write an expression or a product term for each of these rows that has a 1 in the output. To write that product term, I'll consider each of the input variables, and if it's a 0, the variable appears in its complemented form, and if it's a 1, it's going to appear in its uncomplemented form. And then I'll simply OR all of these product terms together to get the final output. So let's do an example. The first row that's a 1 is the second row when the input x, y, and z is 0, 0, 1. So my first product term is x naught ANDed with y naught ANDed with z. Then I'll look at the next row that has a 1. And for this one, it's 0, 1, 0. So the product expression is, or the product term is x naught y ANDed with z naught. Go keep going. The next one is when x, y, and z is 1, 0, 0. So I have x ANDed with y naught ANDed with z naught. Then I come on the next row, and here I have 1, 0, 1. So x, y naught, z. And then the final row when they're all 1, so I have x and y and z. And the sum, or the OR of all of these, equals my output f. And so this is the mechanical way that we can go from a truth table to a Boolean expression by writing an SOP expression, a sum of products. One final note here, if my function has variables x, y, and z, my product terms could look something like one of these. They could also just have 2 of the 3 variables or just one of the variables. All of these are considered product terms. What are not product terms are things such as look like this. X or y is not a product term. Neither is something like this or something like this.